Okay, so we went over chapters 17 and 18 pretty quickly in class, so I said I'd go over them in more detail. Now, chapter 17 is about the limitations of significance tests, and what's significance tests can only tell you whether or not a difference that you see is likely to be due to chance, not whether that difference is something that's important or not. So remember that if we had data on the whole population, if we saw a difference and we had the entire population, no matter how tiny that difference was, we'd say it's significant. Statistically significant. That doesn't mean that you care about it. So here's an example. Suppose we wanted to compare IQ scores of men and women. And so we take a random sample, this huge sample of 10,000 men and 10,000 women, and we find this difference in their IQs of 1 point, 100 versus 101. Well, 1 point, we don't really care about a 1 point difference, but it would be statistically significant just because our sample sizes are so big. Like if we figured out a z-score, remember what z is. Z equals the observed difference, so that would be a 1 point difference, over the standard error for the difference, right? And this standard error would be figured as what? We'd have to figure out the standard errors for each of the samples for the males and the females, and they'd be the same because they have the same standard deviation here and the same sample size. And we're talking about averages, so it would be the SD over the square root of 10,000. So that's 0.2. And then we combine them to get the standard error of the difference. We combine them as the square root of the sum of their squares. And when we did that, we'd get 3.53, which is a huge z-score. So what that means is, just by the luck of the draw, we'd see this result, this one point difference. If we expected the null would be that in terms of difference, that there's no difference in their IQs at all in terms of IQ scores. And when we translate that into a z, because we have such huge sample sizes, the averages aren't going to bounce around when you have 10,000 men and 10,000 women that much. So this 1 point difference, we weren't sure we had no hypothesis about whether males or females were going to do better. Turns out to be this 1 point difference in either direction would turn out to be what? Between 3.53 and negative 3.53. And that's 99.96%. So the chance, our p-value, would just be this tiny little spot on either side. I drew it big so you can see it. But really, 3.53 is really much further out there. And we'd get a p-value equal to 100 minus 99.96, which is 0.04%. That's tiny, hugely significant, but who cares about a 1 point difference? That's what I'm saying. It might not be of any practical importance. So don't confuse practical significance with statistical significance, because with a large enough sample size, any difference, no matter how tiny, can be found to be statistically significant. Because our standard errors, we can make them arbitrarily small by increasing the sample size. But that doesn't make the difference, that tiny difference, important. And similarly, conversely, if our sample sizes are too small, we might not be able to detect an important difference, one we care about. So I just want you to remember that statistical significance and practical significance are two different concepts. Now, the other thing that a limitation of significance tests is that it's very easy to cheat with them. You can do this in many ways, and most the idea, if you understand what significance is, statistical significance, remember that it assumes the null, that the result, that there's the effect you see is just due to chance. And then you calculate the probability that you'd see such a result just by the luck of the draw. So the p-value gives you that chance. So if you run 100 tests, you'd expect 5 of them to result in statistically significant results at the 5% cutoff, null cutoff by definition. So if you run the test 100 times and just show the 5 results that you got to be statistically significant, that defeats the whole purpose. And that would be cheating, or p-hacking is what it's often called. So beware of p-hacking, looking over all the results, data snooping, basically cheating. So that's the idea, and here's some examples of that. So let's say you have this liver cancer is a rare disease, which sometimes is caused by environmental pollutants. And the chance of having 2 or more cases in a given year in a town of 10,000 is small, about 0.5%. So let's say you have a cluster of liver cancers in a small community. So that would be very alarming. But if you go searching through many communities looking for liver cancer, then you're going to find, just by the luck of the draw, you'd find a few clusters, just even if all the towns had no environmental pollutants. So here's a good example of that. Suppose that the EPA reviews the incidence of liver cancer in 1,000 towns of this size over a 10-year period, looking for possible contaminants. Now, how many clusters would you expect them to find just by chance? Well, if you have 100 towns over 10 years times 10 years, that's 1,000 cases, 1,000 town year combinations. And 0.5% of 1,000 is equal to 5. So you'd expect 5 clusters of liver cancer, even when the towns are all clean and have no contaminated water supplies. Of course, what you'd want to do then is to look at these, 5 towns and see if there was an environmental pollutant. But this in itself is not evidence, because you'd expect that. Okay, so that's the idea. And here's another example, is on the next page here. Suppose you did an experiment on ESP and it's repeated 1,000 times. Even if there's no ESP and the experiment's done correctly, how many experiments would you expect to find statistical significance evidence for ESP at the 5% level? Well, by definition, you'd expect 5% of the 1,000, which is equal to 50. So 50 would show evidence even when there's no ESP. So this happens a lot where people run many experiments and just cherry pick the ones that show significant results. And that's cheating. So you can't look over many, many results and then just pick out the ones that are significant. Without reporting how many experiments you ran or looked at. Okay, so that's the idea. And the last thing I want you to remember is that there's nothing sacred or special about the 5% cutoff. It's just a convention. Does a p-value of 4.999 mean anything different than a p-value of 5.001? Not really. It's not like there's no mathematical justification for the 5% cutoff. No. This 5% cutoff is simply a convention. These are basically the same result. And there's no mathematical justification for it. Don't think that there's something special about 5%. Remember how we're deciding this. We're looking often, when we're looking at the normal curve, for example, and we decide that the 5% significance level, we're just saying, okay, at some point we're going to make a decision. We expect, when the null is true, that you'd get around here. At some point we're saying, okay, we're getting enough. It's very rare to see a result this far from the null when the null is true. And we just set this 5%. That just means that this is 5% in the tail or 5% in the two tails for no particular reason. Look, that there's no justification for this because it's a curve. It's a gradual change. The sampling distribution of our test statistic does not drop off. It's not a curve. Think of the sampling distribution. This is what this is. The sampling distribution of our test statistics, if it's a z or a t or a chi-square, is a smooth curve. It doesn't have a sharp dropping off point to justify any particular cutoff. It's not a, it's not a cliff, right? A cliff would look like what? Instead of having something like this, we'd say, okay, we'd expect around here maybe, and all of a sudden there's this sharp drop off that leads to this tiny 5%. It doesn't look like that. It doesn't say, oh, we have, it looks like nothing's going on, and bingo, 5% of the time, all of a sudden we get clear evidence. It doesn't look like that, okay? So those are a few things to keep in mind. All right, so we're going to go over Chapter 18 in more detail too. And we're going to look at type 2 error. We've already looked at the type 1 error. What is a type 1 error? Remember, when we're doing a significance test, we assume the null is true. And let's just look at, let's imagine we're doing a z-test here. And at some point, we assume the null is true here. So this is when the null is true. And then we look at the sampling distribution of our test statistic, and we decide at a certain point, usually the null cutoff, we usually say it's 5%. Let's just say we did that. And this is our typical null cutoff. And right here would be the 5% that we usually set it at. And we're saying, okay, when the null is true, we are going to reject that null 5% of the time. So that's really what we're saying is we're accepting a 5% level of error because we're going to be wrong to reject the null. So this is called a type 1 error, rejecting the null when the null is true. So that's what I say here. The significance level is the probability of mistakenly rejecting the null when it's true, and it's called a type 1 error. And alpha is another is a significance level, and so it's set low to keep the chances of making a type 1 error low. So the null cutoff is called alpha, and our p-value is, if another way of saying the p-value is the p-value we actually get, which if it's less than alpha, we reject the null. So let's write this down. The p-value cutoff, the null cutoff, this is like the null cutoff, is called alpha, the significance level. And it's conventionally set at alpha equals 0.05. For some reason, it's conventionally, they use a decimal here usually, but it's the same thing, obviously, as 5%. Okay? So that's what we're comparing our actual p-value that we get to the cutoff, right? And that's a type 1 error. Alpha, that would be alpha right there, the type 1 error. I'm putting a little alpha in there. Okay, but there's another type of mistake we can make. What about when the null is not true? When the alternative is true? Okay, so then there's another, when the alternative is true, and let's think about it in the context of some example that will help. So let's say we're talking about a fire alarm. Or suppose when the null is true, that means there's no fire, right? So let's just do this example. So there's no fire. And then we have some detection system, some evidence, pretend it's some measure, let's say it's measures this axis right here, let's say measures the amount of smoke in the air. So measures smoke in the air. So when there's no fire, there's generally not much smoke, but of course there's just general smoke, people cooking, smoke, whatever. But at some point it will trigger the alarm. So right here is when there's, all through here, the alarm doesn't go off until the amount of smoke reaches some level, and then it triggers an alarm, and then it's a false alarm here. So a type 1 error is like a false alarm. So let's write that. So alpha is equal to the type 1, and it's usually a Roman numeral they use, type 1 error, and it's like a false alarm. The null says generally there's no effect, and we're triggering this false alarm. But then, let's say there actually is a fire. So when there is an effect, so let's look at when H alternative is true. And now there is a fire. There's no fire. Here there is a fire. Okay, now we're along the same axis. When there's a fire, of course there's going to be a lot more smoke. But sometimes not. So there's a different distribution here of how much smoke is in the air when there is a fire. And there's not much smoke, but there's going to be some overlap between the two. Okay, so they're spread pretty far apart. So the other type of error would be when there is a fire, we're deciding it with this null cutoff. Most of the time it will detect it, but there's still this error right here when it fails to detect it. So when we set this null cutoff, there's two types of errors that we have to consider. And this would be the type 2 error, which we call beta. So that is beta, and that's the type 2 error. And in this case, it would be when the alarm fails to go off, when there really is a fire. So that's the idea. And then there's something else called power, which is 1 minus beta, which is the power to, and that would be, so this is beta, so power would be everything on this alternative curve, 100 minus beta. So it would be this side of the curve, 100 minus beta. And you want the power to be big because that's the power to detect an effect when it's really there. The power that our alarm system would detect a fire when it's really there. So it's the power, so you want a high-powered test. The power to detect an effect when it's really there. So that's what I say here. Now we'd like both types of these errors to be low. We'd like them both to be low. So how could we do that? Well, one way that we could do it would be to build a better detection system that didn't have such that would separate out these two curves more. Maybe by making the standard errors, or making them more accurate. But apart from doing that, if we just want to move this null cutoff, this is what we have given that this existing detective system can't be changed, let's just say that's what we have, well then what we can do is move this null cutoff. But if we move it to make a type 1 error smaller so that the smoke detector doesn't go off and annoy us all the time, we move it over here, well that's going to make the type 2 error bigger, and we definitely don't want to do that. You could have a fire that doesn't have much smoke. So I think the other alternative would be to make the probability of a type of 2 error smaller, and make that really small, because that would be, the consequences of that are very serious, and then just have it would be okay if it's annoying if the smoke detector goes off when you're cooking or etc., but it's not life-threatening. So that's generally what's done. You move it this way. So then you increase it to over 5%. So that's the idea, and let's turn the page here. So if we put this in the context of, sometimes it helps to think of this as a chart. We're making a decision under uncertainty. The overlap of the two curves is uncertainty. So there's a truth out there. There either is a fire or there isn't a fire. So there either is no effect. The null is true, so nothing's going on, no effect, no fire. The treatment didn't work, the null is true, or there is an effect. H naught is false, and there's a real effect. There's a real fire, or the treatment did work, there is a disease, there's something there to detect, and H naught is false. And then we have our decision here to either reject H naught, and we'll reject H naught and say, decide for the alternative, say there's a real effect, right? So our decision is there's something there, there is a real effect. We're deciding that the H naught is false. Or we fail to reject H naught, and we decide that there's no effect. So we can say this is negative here. All right, so when these match up, when there is an effect and we decide there is one, like right here, or there's no effect and we decide there's no effect, these two are fine. We're making the right decision. But when they're opposite to each other, we're making the wrong decision. So what kind of error would this be? This would be like the false alarm or the false positive, the type 1 error. And the type 2 error is what? That would be a false negative. So in all these cases, we're making this decision under uncertainty. We never know for certain what the real truth is, right? So we always run the risk of making one of these types of errors. So in a clinical trial, the null would be the treatment didn't work. In a jury trial, the null would be that nothing's going on, it's just an innocent person. And, in a diagnostic test, the null would be that the person's healthy, that there's no disease. And so the idea is that if you're looking at this chart here, you can only make this type 1 error when the null is true. That's the only time you can make this type 1 error. We can only make the type 2 error when the alternative is true, when the null is really false. So here's another analogy that might help you, and this is the jury trial analogy, where let's look at this. So let's say this axis here would be evidence for whether or not the defendant is innocent or guilty. So let's say for the innocent people, there's a distribution here. There's sometimes a lot of evidence against innocent people just because of bad luck. They happen to be in the wrong place at the wrong time, or they look like somebody else, and there's eyewitness testimony that they did it, etc. But so we have this, at some point we decide, even when the null is true, when the defendant's innocent, we decide that it's beyond a reasonable doubt. And that little bit of a reasonable doubt here, right here, is the type 1 error. But then there's also these guilty people here. And some of them have very little evidence against them, even though they are guilty. Of course, they're shifted way up on this axis, but it's not perfect. So you have to make a decision. So when we decide to, right here, we make some cutoff. The other type of mistake we're making is if the defendants are really guilty, of letting them go. So we're weighing convicting an innocent person compared to letting a guilty person free. So this is your beta and that's your alpha. And we should write that here. So this is the type 1 error, alpha, and here's the type 2 error, beta. So you might say you want to, let's say this was a murder trial, and the consequence would be the death penalty. Well, you want to make that as small as possible. You don't want to kill innocent people. So, but look what happens if you move this over so that you're not killing anybody innocent, when you're hardly ever going to kill an innocent person, look what happens to the other type of error. To the type 2, you're going to let a whole lot of guilty people off. So there's a trade-off between the two. That's what we're saying. And it's you have to consider the consequences of each. Okay, so that's, let's see, what else we have to do in this chapter. So here's the reasoning behind it, that what we just talked about, that the idea is that, you want to set this type 1 error as low as possible, but at some point, we have to recognize that there's a trade-off between the two. So let's see, you should read this, but we just discussed it all, but it's a summary of what we just talked about. And I think, let's just fill out this chart here, that here, the type 1 error is a false positive, right here, and the type 2 error is a false negative. And this is a true negative, right? And this is a true positive. So that's the idea, and that's it.